Thousands of stars can be seen in the night sky when one looks up, far from the lights of cities. Even more stars are visible, but they are too faint for human eyes to detect. All of the stars in the sky are part of our Milky Way galaxy, which has fascinated humans for a long time. The stars, dust, gas, and dark matter that make up the night sky are held together by gravity as we move through space. We are about to embark on an incredible journey around the Milky Way, unraveling its mysteries, wonders, and majesty. You may be familiar with it from your studies of the cosmos, but have you ever wondered what it really is, what makes it up, and where does our solar system exist within it? Astronomers have been puzzled by these basic questions for centuries, and finding answers has not been an easy task. However, beyond the Milky Way's luminous beauty lies a tapestry of mysteries waiting to be unraveled. You may already be aware that our solar system contains 8 planets, the Sun, moons, and various celestial bodies like asteroids and Pluto. However, there is a vast expanse beyond our solar system that you might not be aware of. From Earth, we can see about 6,000 stars without a telescope, which is a minuscule fraction of the total. In fact, for every star that we can see, there are over 20 million that we cannot see. Galaxy systems consist of different stellar remnants, interstellar medium, and star systems. Astronomers estimate that there are 100 billion galaxies in the universe, but they can't be sure because intergalactic space, which contains a thin gas, lies between the galaxies. The Milky Way galaxy contains all of these stars, but there are other larger galaxies, like the Andromeda galaxy, as well. It's easy to see why the universe is believed to be endless when you consider Earth and humans as just a small dot in the vast scheme of things. Radio and X-ray telescopes have helped scientists learn more about the interstellar medium over the last century, and their findings have revealed that it consists of dust, cosmic rays, and extremely diffuse ionized hydrogen atoms, all dispersed throughout dense gas clouds that are believed to be located between 30 and 50 astronomical units from the Sun, where 1 astronomical unit is equal to the distance between Earth and the Sun. The heliosphere, a huge protective bubble formed by the solar wind, surrounds all of these objects, and it acts as an invisible shield, keeping out most of the interstellar material. This disk of debris is known as the Kuiper Belt, and it is located far outside our solar system. Threatening cosmic rays and other celestial debris are ejected into space by the Sun and its planets as they speed through the galaxy. The heliosphere acts as a protective barrier, preventing these harmful particles from reaching Earth. The interstellar space border is located at the boundary of the solar wind, which carries material into the heliosphere along with its own magnetic fields and charged particles. The complex and dynamic structure is created when the solar wind weakens and slows down to about 62 miles per hour when it encounters interstellar space. The wind was previously traveling between 370 and 430 miles per hour. This occurs at the termination shock. The solar wind continues to slow down after the termination shock in the Helios Heath area of the heliosphere. Finally, at the heliopause, the outermost point of the heliosphere, the solar wind stops, and at the heliopore, which is about 11 billion miles or 18 billion kilometers from the Sun, interstellar space begins. Up until now, only 2 spacecraft, Voyager 1 in 1977 and Cassini, have succeeded in reaching this boundary, which scientists consider to be the beginning of interstellar space. This remarkable achievement occurred after 35 years of human space exploration. As we leave the solar system, we'll go through a medium that isn't affected by the Sun. As we approach the triple star system Alpha Centauri, we'll see 3 stars, Alpha Centauri, Alpha Centauri b, and Proxima Centauri. Alpha Centauri AB is a binary star system consisting of 2 main stars, Alpha Centauri A and Alpha Centauri b, which are Sun-like stars classified as class plus G and K, respectively. Alpha Centauri b is the 3rd brightest star in the night sky and the brightest star in the constellation. It has a z-score of 0.9 and less than 0.5 solar luminosity, while Alpha Centauri, has 15 times the luminosity and 11 times the mass of the Sun. Alpha Centauri A and B have a 79-year orbital period around a shared center, and the distance between the two stars fluctuates. Proxima Centauri, a red dwarf star, is the most common type of star. It is about 7 times smaller than the Sun and slightly more than half the size of Jupiter. Robert Innes, a Scottish astronomer, discovered the star in 195. The star's eccentric orbit causes its distance from the Sun to vary from 356 astronomical units, which is roughly Pluto's distance from the Sun, to 112.0, which is Saturn's distance from the Sun. Although the Alpha Centauri system is visible in Centaurus, Proxima Centauri is typically invisible to the naked eye. It orbits the other two stars in the system, Alpha Centauri A and Beta Centauri B, and has a temperature of 3,100 Kelvin, compared to 5,772 Kelvin for our Sun. This tiny star is barely half the size of Jupiter, and red dwarf stars like it have long lifetimes due to their efficient consumption of hydrogen fuel. It takes 550,000 years for B Proxima Centauri to complete an orbit around A and B. With an apparent visual magnitude of 11, it is the dimmest of the three stars. Proxima Centauri is a flare star, meaning its brightness can change by more than 1 magnitude in a matter of minutes. These flares, which occur multiple times a day, can be powerful enough to make Proxima Centauri explode. Centauri, which is visible to the naked eye, released the strongest solar flare ever seen in the Milky Way galaxy in 2019, appearing 14,000 times brighter in ultraviolet light than usual. Despite outliving the Sun, Proxima Centauri will ultimately meet the same fate as all stars. It will burn up into a white dwarf star when its hydrogen supply runs out. Astronomers have detected this stellar death in 2022. There are 3 planets in close proximity to Proxima Centauri: Proxima b, Proxima c, and Proxima d. These planets are considered to be in the habitable zone, which is the range of distances from stars where a planet's water, if any, could be liquid and support life. Proxima Centauri b was found in 2016, and its mass is estimated to be around 177% greater than Earth's, suggesting that it is likely rocky. Despite being 20 times closer to Proxima Cent than Earth is to the Sun, Proxima Centauri b is still within Proxima Cent's habitable zone. It orbits Proxima Cent every 11 Earth days at a distance of approximately 0.0490, making it tidally locked like our Moon, with one side always facing Earth. Since it is far closer to Proxima Cent than Earth, it is possible that the opposite side contains liquid water, but its habitability is uncertain because of the intense radiation and flares from Proxima Centauri b's host star make it feel the gravitational pull of its stars far more strongly than Earth feels the tidal effect of our Sun. The Moon, being much closer, also exerts a stronger tidal force than the Sun. Since tides can move air as well as water, it's plausible that the tidal pull on Proxima Centauri b's atmosphere is up to 500 times stronger than Earth's. As a result, it's likely that Proxima Centauri b is nearing the maximum. Proxima Centauri Ca, a mini-Neptune exoplanet that was first thought to have been discovered in 2019, appears to shine much brighter than Earth and is approximately 7 times larger than our home planet. It orbits its star once every 1,900 Earth days, providing a formidable tidal force that few planets can withstand while maintaining a solid surface. Given its size, the planet may be encircled by a ring system or covered in dust clouds. Astronomers predict that the planet's temperature is near minus 233 degrees Celsius, making it uninhabitable. The star was first detected in 2019 after the gravitational pull of Proxima Centauri C caused its parent star's velocity to wobble. In 2020, images taken by the Hubble Space Telescope in 1995 confirmed Proxima Centauri's existence. Making it one of the rare exoplanets with visual confirmation. In 2022, a third planet was found orbiting Proxima Centauri. This exoplanet, known as Proxima Centauri d, contains about 25% of Earth's mass and orbits its star at a distance of roughly 3% of Earth's distance from the Sun additionally. In 2021, scientists observed that Proxima Centauri d was among the lightest exoplanets. Discovered what might be the first signs of an exoplanet in the habitable zone of Alpha Centauri, also known as Rigil Curis. The planet, candidate C1, is thought to have a mass between half of Saturn's and Neptune's, and it orbits Alpha Centauri at a distance of about 11.0. Direct thermal imaging revealed that C1 had an elongation of around 0.1 arc, making it appear as bright as a giant planet. This finding is in line with the orbital motion of a planet in a 70 degrees orbit and the fact that C1 is located in Alpha Centauri's habitable zone, which could include a miniature Neptune or even a super-Earth, adds an intriguing dimension to the discovery of this exoplanet. We can almost certainly find Earth-like planets in the Alpha Centauri system, but the big question is, could humans ever actually live there? The greatest challenge in our pursuit of establishing a new home in the Alpha Centauri system will be traversing the immense distance to reach these three stars. Even at the steady speed of the Space Shuttle Discovery, which was retired in 2011, it would take more than 148,000 years to reach Alpha Centauri, which is more than 4 light-years away, or about 235 trillion miles or 378 trillion kilometers. To overcome such a vast distance, another, more powerful spacecraft would be required. NASA estimates that even when the Orion spacecraft, the crew capsule connected to the Artemis program, is ready to launch, it will still take more than 148,000 years. Carry humans, its top speed is about 20,000 miles per hour, which won't drastically reduce the time it takes to travel to Proxima Centauri. And that's assuming neither of these spacecraft was intended for relatively short trips to the Moon or Mars. As we've already established, the only spacecraft to leave the solar system are Voyager 1 and 2, and even at their maximum speed of over 35,000 miles per hour, it will take them nearly 40,000 years to travel 2 light-years. Spacecraft need to be incredibly small and robotic to reach distant stars in a reasonable amount of time, like within a generation. They also need an extremely strong energy boost to get up to speed. The basic idea behind the Breakthrough Starshot is that these spacecraft might take more than 880,000 years to approach Proxima Centauri, considering that light takes more than 4 years to reach Alpha Centauri. Project involves building a nanocraft called a star chip that is equipped with light sensors. It would then be sent into Earth orbit by the mother ship. The probes would be released one by one and guided by a massive ground-based laser array. The biggest obstacle is the Earth's atmosphere, which distorts both the laser and incoming light, making it difficult to apply the force needed to propel a spacecraft forward. However, with the help of more powerful lasers on the ground, the space mission could be kept in close focus. Miniature lasers affixed to spacecraft that could assess atmospheric impacts in real time and launch the vessel whenever needed. The power consumption of these lasers would be equivalent to the entire U.S. electricity consumption, but they only need to run at full power for 10 minutes. To disperse this power over a 1-kilometer square area, the Starshot team intends to use 100 million lasers. Once the lasers are turned on, they intend to push the limits of space exploration. At a speed of over 130 million miles per hour, 216 million kilometers per hour, the object hurtling through space will be traveling at a staggering 20% of the speed of light. Its diameter is just over 10 meters. If all goes well, this spacecraft could reach Alpha Centauri in around 22 years. However, it faces serious challenges in navigating the solar system and may be significantly slowed down by interstellar debris. Even if it does reach Alpha Centauri, it will take 4 more years for its signals to reach Earth. Music. Alpha Centauri is slowly approaching Earth, but does not pose any threat. The distance between Alpha Centauri and Earth is currently 326 light-years, and it will be at its closest in 29,700 years, at which point it will be about 3 light-years away. Throughout a human lifetime, this gradual change in distance will not affect Earth or the solar system in any noticeable way. We continue to learn more about space every day as we move on from Alpha Centauri to the Barnard star, the second nearest star to the Sun, which is located at a distance of. Its 595 light-year diameter is named after the American astronomer Edward Emerson Barnard, who made the discovery in 1916. Barnard star is believed to be 11 to 12 billion years old, or about twice the age of the Sun. As a red dwarf star, it is likely a thick disk member of the Milky Way. Flares, which can double a star's brightness, are produced by young or middle-aged red dwarfs that spin fast enough. However, Barnard star is too old to exhibit this type of behavior. While William Cochrane of the University of Texas at Austin was attempting to obtain the star spectra using the 27M telescope at McDonald Observatory in the hopes of finding alterations that would indicate the presence of planets in orbit, he instead observed emission lines in the spectrum, suggesting that the star could be. The Cochrane team's investigation 4 years later found that the star's hot blue flare was comparable to those of younger red dwarfs, despite its great age. The flare's temperature was at least 8,000 Kelvin, which was twice as hot as the star's 3,100 Kelvin temperature. As the Barnard star approaches Earth, its distance from us decreases by 36 light years per century at an incredible speed of 108 kilometers per second, or 67 meters per second. By the end of the century, it will have dwindled to just 385 light years. Because of its proximity and enormous proper motion, roughly 104 arcs per year, or the equivalent of a lunar diameter every 180 years, Barnard star is a prime target for exoplanet searches, as any systematic variations in its motion across the sky caused by planets in orbit would be more noticeable. The star has been the fastest-moving star in Earth's skies by 11,800 AD. In 2018, the planet was observed orbiting Barnard star at a distance of about 60 million kilometers, or 37 million miles, on a 233-day orbit. Its mass is at least 32 times that of Earth, but the planet is not in the habitable zone because the star is not very bright, so any water on its surface would likely be frozen. As we move farther away, around 86 light years, near the constellation of Orion, we locate Sirius, also known as the Dog Star or Sirius, the brightest star in the night sky. Sirius has a mass twice that of the Sun and has. Sirius, a binary star in the Cusp major constellation, has a surface temperature of nearly 18,000 degrees Fahrenheit, a bluish tint, and is 25 times brighter than the Sun. It is easily visible in the winter night sky of the northern hemisphere, and the ancients were familiar with the star because of its size, 15 million miles, 24 million kilometers, and the fact that it would outshine our Sun by more than 20 times if they were placed side by side. Sirius B is a companion star to Sirius, and its discovery in 1862 shocked astronomers. Sirius is so bright that it can be seen with the naked eye, but Sirius B is 10,000 times fainter. In 2005, using data from the Hubble Space Telescope, astronomers were finally able to estimate the mass of this faint object, which is extremely difficult to observe from Earth. Within 20 light years of the Sun, there are approximately 131 objects, including stars brown. There are a total of 131 objects in 994 stellar systems. 22 of these are visible stars, defined as having a luminosity of at least 65 apparent magnitude, which means that they cannot be seen without a telescope. Of these, 103 are main sequence stars, 80 are red dwarfs, and 21 are brown dwarfs. One of these, Y08550714, is a sub-brown dwarf that may be a rogue planet. The following celestial bodies have reached their final stages of star formation: 6 white dwarfs, 1 red dwarf candidate called Schultz's star, and a companion brown dwarf. Approximately 70,000 years ago, they passed close to the edge of the Oort cloud. At present, they are about 22 light years from the Sun. It is highly probable that their passage triggered a comet storm, the arrival of which will take more than 1 million years. The event affected the orbits of several stars, including the type star HD. According to the second data release from the Gaia telescope, 694 stars will approach our solar system in the next 15 million years, with 26 of them expected to arrive within 33 light years and 7 more within 6. 7977 has also been studied. It had a close pass about 28 million years ago and is now situated about 247 light years from Earth. There will be more stars in the future, of course. Gliese 710 is one of the most famous examples of a star that will soon pass very close to Earth. It is an orange star that is about 60% the size of the Sun and is located in the Serpens constellation. The sheer number of stars that need to be studied makes this estimate likely much higher. For instance, a star that was en route to our solar system 10 million years ago would be 600 to 6,000 light years away from the Sun today, but millions of stars are already much closer. In 129 million years, at a speed of 5,499 km per hour, or nearly 32,000 miles per hour, Gliese 710 will pass the Sun at a distance of around 10,520 astronomical units. This is more than 100 times the distance to Pluto, which orbits the Sun at an average of 395. Nevertheless, it could still cause problems for the solar system as a whole. Even if it only affects the outer solar system and nothing within 40 should be affected. However, it is still within the realm of possibility that it may disrupt the Oort cloud, as it is highly likely to pass through it for millions of years. As a result, comet showers could form as they head toward the Sun, potentially resulting in around 10 comets visible to the naked eye each year. Looking for stars near the Sun could present an opportunity to discover ancient comets, as well as to foretell an intriguing future for Earthlings millions or even thousands of years from now. The local interstellar cloud, the local bubble, which is approximately 30 light years across, is where our solar system and other stars and dwarfs are currently moving. It's an oddly shaped cavity in the interstellar medium, approximately 1,000 light years across. The Sun was far away when the bubble formed, but about 5 million years ago, its path entered the bubble. Stars formed on the bubble's surface, not inside, though. A total of 88 modern constellations can be found, including Orion, which is named after the Greek mythological figure of the same name. It contains more than 60 stars, including Betelgeuse, a red supergiant star situated at 1344 light years from Earth. The 7 star-forming regions surrounding this bubble are responsible for making life on Earth possible. Situated at a distance of approximately 650 light years, this star is one of the largest known to exist. Its diameter is approximately 767 million miles, or 12 billion kilometers. The star is roughly 700 times larger than the Sun and has a mass ranging from 10 to 20 times that of the Sun. The possibility that Betelgeuse has less than 300 years of fuel remaining in its core has sparked ongoing debate about the possibility of an explosion. As the star burns through its remaining fuel, its core collapses into a black hole, releasing its outer layers at speeds of up to 25,000 kilometers per second. Supernova explosions, which can reach speeds of up to 40,000 kilometers per second, are awe-inspiring for onlookers on Earth. In the case of Betelgeuse, the layers of gas and dust will illuminate our sky for weeks, rivaling the brightness of the full moon. The catch is that most astronomers don't think Betelgeuse is ready for a big explosion just yet. They typically anticipate that it will explode within the next 100,000 years or shortly afterward. In cosmic time, there are 3 famous stars in the constellation Orion: Alnitak, Allen, and Menaka. These stars are located in the constellation's center and are visible from all over the globe. Orion's belt is perhaps the most recognizable feature of the constellation, and the 3 stars in it are each thousands or tens of thousands of times brighter and several times more massive than the Sun, even though they appear to be closer together than they actually are. The Orion Nebula, also known as M42, is one of the most visible Messier objects in the sky. It is located below Orion's belt and is easily visible with a telescope or binoculars. Looking at it is like looking into a celestial nursery where new stars are born. The Orion Nebula is one of the largest gas and dust clouds in our Milky Way galaxy, and it is about 2 million light years across. Located approximately 1,300 light-years from Earth, the magnificent nebula is a young, open star cluster with stars that are only loosely bound by gravity. With an apparent brightness of +4, it is even visible to the human eye on the astronomical magnitude scale, and it is the faintest object that, under ideal lighting conditions, can be seen by the naked eye. The nebula's diameter ranges from 30 to 40 light-years, and it may be giving birth to 1,000 stars within. A group of astronomers from around the world proposed in 2012 that the Orion Nebula star cluster, which forms in a gas cloud, may contain a black hole at its core. Using tiny telescopes, you can make out the 4 brightest stars in the nebula, which make up the trapezium. The nebula is lit up by these young, hot trapezium stars, which are relatively young stars, having only been around for about 1 million years. Here's an infrared image of the Orion Nebula. Last year, the James Webb Space Telescope captured a nebula that looked like an explosion of dust, stars, and clouds in red, purple, and blue against a black background. Inside the nebula, the telescope found 540 planetary mass objects, the largest of which were Jupiter itself. Among these planetary mass objects, the most interesting were the Jupiter mass binary objects, which aren't really objects at all, but rather binary systems. Discoveries made possible by NASA's Spitzer Space Telescope using infrared imagery have led scientists to believe that there are just 2 major arms dominating the spiral structure of the Milky Way, rather than the 4 that were previously believed. Spiral galaxies, which resemble flat, rotating disks with bulges in the center and spiral arms extending outward from a bulge, are common in the universe. The 2 major arms of the galaxy, Centaurus and Perseus, can be seen at the ends of a thick central bar. The 2 minor arms, Norma and Sagittarius, are located in the middle and are less noticeable. The minor arms are primarily gas, and the areas where stars are being formed in the major arms have the highest densities of young and old stars. Radio astronomers study the motions of the hydrogen clouds that follow the arms at an angle of about 9 degrees. In contrast to the Scutum Centaurus arm, which is approximately 55,000 light-years long and 1,000 light-years wide. The Perseus arm is more than 60,000 light-years long and features the famous Crab Nebula and double clusters. Our solar system is located between these 2 prominent spiral arms, but we aren't exactly floating aimlessly in space. In fact, we're right on the edge of the Orion Cygnus arm. This small spiral arm, which goes by several names, is named after the constellation Orion. It is approximately 10,000 light-years long and 3,500 light-years wide. A 2016 study found that its length might be more than 20,000 light-years. Our solar system is situated in the local bubble on the inner edge of the Orion arm, which is situated 26,000 light-years from the galactic center. You might be surprised to hear that. It is estimated that the Sun has completed only 18 to 20 orbits since the beginning of mankind, as the solar system orbits the Milky Way at a speed of about 220 kilometers per second, or 0.73% the speed of light. At this speed, it takes around 1,400 years to travel 1 light-year, or 8 days to travel 1 astronomical unit following the ecliptic. The Sun's 250 million-year rotation is called a cosmic year or galactic year, is making its way toward the zodiacal constellation Scorpius in the Milky Way. The last time this happened, dinosaurs were still living on Earth. Who knows when this will happen again? It's important to know where we are in relation to the galaxy, because, similar to planetary systems, galaxies appear to have habitable zones. This is because many solar systems in our own Milky Way orbit the galaxy along paths that take them through dangerous spiral arms, and a staggering 95% of these stars might not be able to sustain habitable planets. The radiation from all those stars is too much for any star that goes through one of these stellar swarms. To stay in sync with the rotation of the galaxy, our solar system stays far enough away from the galactic center to remain in the Karma region, which is between the spiral arms of a big and complex galaxy. Here, Earth and its planetary siblings are in a peaceful resourcer region. As we approach the galactic center, located in the Scutum constellation, approximately 9,500 light-years from Earth in our Milky Way galaxy, we will eventually come across Uy. This hypergiant star is one of the biggest known stars, with a radius of 118 billion km, 1,700 times larger than the Sun's radius. Therefore, the star would have a diameter of more than 8 astronomical units, or 150 million kilometers, 93 million miles. The immense size of this star also means that its outer surface would. The gas nebula ejected from the star extends 400 times the distance between Earth and the Sun, far beyond Pluto's orbit. To put another way, a sphere the size of Uy could fit more than 5 billion suns, but the Sun itself could only hold around 1 million Earths. Unsurprisingly, Uy is classified as a hypergiant star, the third highest classification after regular giant and supergiant. It may be the biggest star in terms of size, but it isn't the heaviest or most massive star either. Mass is a measure of the amount of matter in a star. The heaviest star is our 136A1, which is 300 times the mass of the Sun, but only 40 times the radius. In contrast, Uy is much larger than the Sun despite having a mass between 7 and 10 times the Sun's. Just because Uy is massive doesn't mean it's hotter than any other star. Interestingly, Uy surface is nearly half as hot as our Sun's. What's more, it's a variable star, meaning its luminosity can change over time. This is because the material at and near the surface is constantly fluctuating due to the unstable battle between gravity and fusion. Astronomers love stars like Uy because they teach us about the inner workings of stars, and it's believed that it can. Sustaining a planetary system, it's likely that the innermost exoplanets have already been engulfed by the host star's expansion. What's more, our star is so dim that it's highly unlikely that we will ever get a clear look at those exoplanets. As we travel towards the galactic center, approximately 26,000 light-years away, we catch a glimpse of the celestial mystery known as Sagittarius A. This supermassive black hole is an incredible cosmic monster. Its estimated mass is incomprehensible. At a staggering 43 million times the mass of our Sun, this gigantic monster is situated at the center of our spiral galaxy, the Milky Way. Black holes are regions of space so densely populated with mass that nothing can escape from them, not even light. While we can't see black holes directly, telescopes can detect the material surrounding them, which can include gas and dust. Black holes, when they expand and emit detectable radiation, can sometimes be seen by telescopes as they affect the motions of nearby stars. However, observing Sagittarius A directly is extremely difficult due to a thick cloud of dust that blocks out light. Fortunately, astronomers have come up with clever ways to overcome this cosmic barrier. In April 2019, the Event Horizon Telescope, a network of radio telescopes covering an entire planet, achieved a historic first by successfully obtaining the Sagittarius A, a less massive and over 1,000 times smaller black hole than M87, was visible in the photograph as a faint outline against the brilliant background. The accretion disk, which feeds the black hole, causes occasional X-ray flashes. This discovery follows the 2019 release of the first picture of M87, the black hole at the center of the farther away Messier 87 galaxy. The gas disk that surrounds the supermassive black hole in our galaxy can reach temperatures of 18 million degrees Fahrenheit, 10 million degrees Celsius, and it spins at nearly maximum speed, devouring everything in its path. To measure its rotation speed, physicists use NASA's Chandra X-ray Observatory to study X-rays and radio waves from material outflows. A black hole in the Milky Way has a spin speed, abbreviated as A, that can be anywhere from 0 to 1. 1 is the maximum rotational speed for a given black hole and represents a substantial fraction of the speed of light. As an example, physicists have found that Sagittarius A rotates at a speed between 0.84 and 0.96, which is close to the upper limit determined by the black hole's width. Unlike solid objects like planets, stars, and asteroids, which have actual surfaces, black holes distort space-time as they spin, pulling anything in their ergosphere with them. This phenomenon is called frame dragging or the lensing-Thüring effect, and understanding how space behaves around a black hole requires knowledge of its spin. Another consequence of frame dragging is the electromagnetic radiation they emit. Peculiar optical phenomena. The light's trajectory is bent or distorted as it nears a spinning black hole because of the curvature of space-time. This phenomenon is called gravitational lensing, and it happens because the gravitational pull of the black hole twists the light's trajectory. Other effects, such as frame dragging, can cause the creation of light rings and even the black hole shadow. In terms of matter and its growth, the angular momentum of a black hole increases as more matter falls into it. However, there is a limit to how much angular momentum a black hole can have. Another factor is the mass of the black hole. Larger black holes are more gravitationally attracted, making it harder to spin them up. This may explain why the first black hole ever recorded, the rapidly feeding supermassive black hole at the center of galaxy M87, is spinning at a rate of 0.89 to 0.91 despite its mass of 65 billion suns, and Sagittarius A, which has a mass of about 45 million suns and a spin speed of 0.84 to 0.96, is commonly thought to be a black hole. However, during the course of their research, some scientists began to suspect that Sagittarius A might not actually be a black hole, but rather an enormous concentration of dark matter. This would explain our galaxy's basic structure. Despite widespread belief, Sagittarius A has never been officially confirmed as a black hole. Put simply, it is an incredibly bright radio emitter situated at the center of the Milky Way galaxy. Recently, astronomers faced a difficult situation involving the G2 gas cloud, which had drifted dangerously near to Sagittarius A. Despite the fact that the supermassive black hole was supposed to have pulled it in and destroyed it, the cloud continued to drift aimlessly. By studying the interaction between the two, astronomers were able to deduce that G2 was no ordinary gas cloud, as its lack of effect could be observed. Explained that in order for the cloud to avoid being devoured by the black hole, two things had to be present. First, a long, thin, cold gas cloud, and second, a very small, dusty object-like segment that dominated the detected emission from G2. However, astronomers may be more worried about the possibility that Sagittarius is not a black hole at all. This intrigued them so much that they created a simulation of our galaxy to test this theory. Researchers have discovered that the Milky Way galaxy continues to exist and function in a similar fashion even after the galactic center has been replaced. In their simulations, they have found that the behavior of the rotating curve in the outer halo of the Milky Way is identical to that of nearby stars, or those linked to the radio source Sagittarius A. Taking their inquiries a step further, they have proposed that darkos, a family of particles related to fermions, may make up the mass at the center of the galaxy. Sagittarius A, in particular, would exhibit black hole characteristics if it merged with its dark counterparts, which are largely dormant and only infrequently absorb gas or dust. Despite this, it is believed to have a mass millions of times greater than our Sun. Many questions remain unsolved about this supermassive black hole, but future observations from the Event Horizon Telescope should help to clarify these mysteries. Since there are no stars big enough to directly collapse into a black hole of this size, scientists are stumped as to how supermassive black holes like Sagittarius A come to be. One theory is that smaller black holes merge to form larger ones, or another is that smaller black holes grow tremendously large by consuming gas and dust from their surroundings. Either way, the process is mysterious. In 1997, American astronomer Harlow Shapley found the first reliable measurement of the galaxy's size. Shapley disproved previous beliefs about the globular cluster's spatial distribution and found that the galaxy is massive, with the Sun closer to its periphery than its center, rather than a relatively compact arrangement. Sagittarius A is still a cosmic mystery at the heart of the Milky Way, but our knowledge is expanding and we are continuing to uncover its secrets. His calculations have been very accurate throughout the years. The Milky Way stellar disk is about the size predicted by Shapley's model. Dark matter, also known as invisible matter, may fill an even larger volume than anticipated, and neutral hydrogen is somewhat more widely distributed. The system assumes that globular clusters surround the galaxy. The Sun is located about 30,000 light-years from the galaxy's center. Recent calculations suggest that a dark matter area with a small number of visible stars could have a diameter of approximately 2 million light-years. This area would also contain numerous satellite galaxies. Our galaxy, the Milky Way, is part of the local group of galaxies, which is a subcluster of the Virgo supercluster, which is a part of the Luna supercluster. Our galaxy contains between 100 and 400 billion stars, and at least that many planets. The radiation from the Big Bang is causing everything in space to be in motion. Astronomers utilize the cosmic microwave background, CMB, to determine the velocities of space objects. The Milky Way galaxy, which is part of the local group of galaxies, is believed to be moving at a speed of about 600 kilometers per second, or 372 meters per second. This is because the Milky Way's oldest stars are nearly as old as the universe itself, and they most likely formed in the early stages of the Big Bang. From outside the nuclear zone, gas is being pulled into the black hole by its strong gravitational force. As it gets closer, the gas is squeezed into a rapidly rotating disk that extends outward about 5 to 30 light-years from the black hole. The data clearly show that matter, including gas from the z direction, which is perpendicular to the galactic plane, is being drawn into the black hole. Around the nucleus, there is an extended bulge of stars that is spherical and mostly made up of stars in population 2, despite the fact that they are relatively rich in heavy elements. Stars are classified into 3 main populations based on their metallicity, or the amount of elements heavier than helium in their composition. The oldest population is population 3, which includes the oldest stars in our solar system. Population 1 stars, which range in age from 0 to 10 billion years, are located in the disk portion of the galaxy, while the younger stars in population 2 are in the spiral arms. The orbits of the youngest stars in each population are. Stars in this population tend to be more organized and follow more or less circular paths through the galactic disk and its midplane. Open clusters formed by young stars in this population are referred to as such because their stars are not tightly packed together like the old concentrated globular clusters. Stars in this population also tend to have a higher abundance of heavy elements, which astronomers often refer to as metals. The oldest stars in this population also tend to have somewhat eccentric orbits, which may transport them up to 3,000 light-years from the dispersion plane, and their metal abundance is 0. 2 stars in the population, with masses less than or equal to 0.8 solar masses, inhabit the spheroidal component, the stellar halo, and bulge. Their ages range from 10 to 13 billion years, and their orbits are significantly more elliptical and randomly oriented than the population ones. As a whole, the spheroidal component has little overall rotation. The globular clusters were utilized for the purpose of pinpointing the galactic center due to their characteristic swarming behavior, similar to beehives. In contrast, the so-called population 3 stars have not been directly observed and are therefore believed to contain almost no heavy elements. These stars were likely the first to form in the early universe, just after the Big Bang, when they were incredibly massive and hot, rapidly converting hydrogen and helium into heavier elements through their fuel combustion. The stars in our galaxy are surrounded by a massive hot gas halo that extends several 100,000 light-years in all directions. When stars die, they explode as supernovae, releasing some of their elements into space. These stars likely formed the first heavy elements that later stars would contain, and they likely played a significant role in the formation of the first galaxies. According to the Parano Observatory, the stars in the inner halo are around 115 billion years old, while the stars in the outer halo are believed to be the stellar components of smaller galactic systems. The outer halo is composed of older stars with lower metal content, and its diameter is around the same as that of the Milky Way. Astronomers believe that the mass of the Milky Way halo is approximately equal to the total mass of all the stars in the Milky Way. The Milky Way's halo, which contains gas and dark matter in addition to stars, provides evidence of a billion-year-old collision between two galaxies and lends credence to the idea that the Milky Way's origin story is dynamic. Within the Milky Way's stellar halo, astronomers have discovered over 200 variable stars, or Lyra stars, which are important for measuring astronomical distances and are frequently found in globular clusters. With a distance of nearly half the distance to Andromeda, the farthest star from Earth is approximately 1 million light-years away. Of the total matter in our galaxy, 90% is dark matter, or invisible to the naked eye. The remaining 10 to 15% is visible stuff, mostly gas and dust. Simulations of the Milky Way's rotation have revealed that this enormous quantity of dark matter creates an invisible halo. Without dark matter, the stars within the Milky Way would be visible. If the Milky Way were to orbit at a significantly slower rate than what has been observed, the dusty ring would be visible in the night sky on clear nights. However, because our galaxy is located about 26,000 light-years from its center, we cannot take pictures of its disk. So any representation of it you have seen is either an artist's interpretation or a different spiral galaxy. Since we can only take pictures of the Milky Way from inside the galaxy, how come we know that it is a barred spiral galaxy? Music. Several clues point to the Milky Way's shape. One is the bright band of stars that stretches across the sky in places with dark night skies. This band can be seen with the naked eye and is produced by the Milky Way disk, which tells us that our galaxy is essentially flat. Several telescopes on Earth and in space have taken pictures of this disk by capturing a series of images taken from various angles, like a panoramic shot on a smartphone, provide more proof that our galaxy, the Milky Way, is spiraling rather than elliptical. If our galaxy were elliptical, our stars would appear scattered across the sky, not concentrated in one band. Up until about a century ago, the Milky Way was widely believed to be the entire universe, despite the fact that other galaxies had. Discovered in the 17th century, the first galaxies were initially thought to be small objects within our galaxy. However, French astronomer Charles Messier, who was an expert at observing comets, noticed other fuzzy objects in the sky and was sure they weren't comets. He compiled a list of 110 star clusters and spiral nebula to help other comet hunters avoid being misidentified. The fuzzy spiral nebulae were not recognized for nearly 300 years. Some astronomers believe they were island universes or objects similar to our Milky Way galaxy, but outside of it. Others disagreed and believed the nebulae were really gas clouds from our Milky Way. The debate didn't end until the 1920s, when American astronomer Edwin Hubble measured the exact distance to a spiral nebula. Hubble found that, in 1923, while studying the Andromeda Nebula, now called the Andromeda Galaxy, he actually caught a glimpse of a Cepheid variable star. These stars, whose brightness changes periodically over time, were first identified in the early 1900s by American astronomer Helen Ritchie. Leavitt later found a relationship between a star's luminosity and its period, which is now called the period luminosity (PL) relationship. This relationship can be used to calculate the actual brightness of a star. This put an end to the controversy surrounding the spiral nebulae and proved that they were in fact distant galaxies similar to the Milky Way. Hubble continued his study of galaxy distances using seeds as his measuring tool before publishing his results in. He determined that the seed he was studying in M31 was located outside of our own galaxy by calculating its period, which is obtained by measuring changes in brightness over a period of days or weeks. The recessional velocity of galaxies is inversely related to their distance from us. Farther galaxies recede more rapidly than closer ones. This relationship was later called Hubble's law. In 1929, Hubble plotted the distances from CI variables against the velocities of galaxies, which were determined by estimating the redshift of their spectra. Most galaxies are receding from Earth, according to this graph, enormously high because, Back then, astronomers didn't know that there were multiple kinds of stellar variables with slightly different period-luminosity relationships. However, with the advancement of modern astronomy, the value of the slope of the graph, Hubble's constant, has been lowered, and the findings are now convergent toward an accepted value of approximately 65 kilometers per second. This means that galaxies recede an extra 65 kilometers per second for every megaparsec that they are away from us. The universe is filled with trillions of galaxies. There are hundreds of billions of stars in every galaxy. Just as studying atoms helps us understand materials, studying galaxies helps us understand the universe. While research into galaxy formation dates back about 50 years to the groundbreaking work of Egan, Linden, Bell, and Sandage, our current understanding of how galaxies form is incomplete. As we delve deeper into the formation and evolution of galaxies, we uncover numerous unanswered questions, such as our origins and future. By studying galaxies other than our own, we can deduce various conclusions regarding the universe's evolution. However, since other galaxies are too distant for us to observe their stars in great detail, we can only draw conclusions about our own galaxy. If our understanding of the Milky Way's development can shed light on other galaxies, then we will have a solid foundation upon which to build our knowledge of the universe as a whole. Just after the Big Bang, which happened 1,361% of the time ago, the Milky Way started as one or more small overdensities in the early universe. Now, about half of the stars in the modern universe reside in galaxies like the Milky Way. The Milky Way's stellar halo is composed of star groups and individual stars that originally belonged to other galaxies. The Milky Way's mass eventually reached a point where it started to rotate relatively quickly, due to the conservation of angular momentum billions of years after the first stars were born. Some of these overdensities were the seeds of globular clusters, where the oldest stars in the Milky Way now formed. It's possible that approximately half of the Milky Way's material came from distant galaxies. The gaseous interstellar medium was compressed into a disk from a roughly spheroidal shape due to momentum. As a result, subsequent star generations formed in this spiral disk. The Milky Way has grown to its present size and shape by absorbing numerous galaxies. In the past 12 billion years, it has swallowed up over a dozen galaxies, according to cosmological simulations. Around 11 billion years ago, it merged with a particularly massive galaxy called the Kraken. Presently, it is consuming. Milky Way and Andromeda are the two biggest galaxies in the local group. They will merge because they were gravitationally bound before dark energy took over. The merger is expected to alter the night sky over Earth. Currently, the Milky Way is traveling at a speed of 250,000 miles per hour towards the Andromeda Galaxy. The two galaxies are expected to collide in about 45 billion years, at a spot in space about halfway between it and the Andromeda Galaxy, which is quite a distance from Earth, 25 million light-years. So even though it's hard to believe, experts believe that our solar system will likely survive such a terrible event. This is because galaxies are mostly empty space, and even though our galaxy and the Andromeda Galaxy both contain 100 billion stars, the collision won't have much of an effect on our solar system. It accelerates faster as it approaches Earth. Andromeda will be pulled closer and closer by the Milky Way's growing gravitational pull. In just 4 billion years, the Milky Way and Andromeda will have yoked and torn at each other's throats, leaving behind only the spectral framework of two separate galaxies in the past. The destruction will continue indefinitely until the central supermassive black holes in both galaxies are close enough to collide. Once the Milky Way and Andromeda galaxies merge, our solar system will find a new home in an elliptical galaxy, a completely different type of galaxy. But what about Earth? Will life here continue after the merger? Well, in about 75 billion years, the Sun will grow bigger and eventually swallow Earth, turning it into a red giant. This process will ultimately take about 4 billion years as the amount of solar radiation reaching Earth's surface increases. The runaway greenhouse effect, similar to the one occurring on Venus at the moment, could cause temperatures to rise, making Earth an uninhabitable planet after the merger. On the other hand, maybe by that point in time, Earthlings will have mastered space travel, and we'll have left our solar system behind. In that case, we could still be able to see Andromeda colliding with the Milky Way, but from a slightly different perspective. Looking up, let's not forget how brief our lives are. We, the stardust children of the universe, have gazed into the vast black void for billions of years, marveling at the cosmic tale that has unfolded before us. For whatever reason, we find ourselves here, sitting and wondering.